Hi, good evening, everybody. Good evening. I don't think my network is terrible. My network is okay. My network is very okay. So I'll be starting in the next 3 minutes. So you can share the link with your friends so they can join. We are starting in the next 3 minutes. So you can share the link with your friends so they can join. Good evening. I can see Rosaline Ebo. Yeah. Good evening, Miss. I can see Dara Solo. Hi, good evening. Felicia Sampson, good evening. Who is okay? Dara Solo, network is not bad. Check your network. I can see Duke Hope. Good evening, my brother. Rosie, okay. Don't worry, network is going to be okay. You can refresh your phone network again. Maybe put it on flight mode and restore it again. It should be okay. So we are starting in the next 3 minutes. Please share the link with your friends so they can join. We are starting almost in the next 5 minutes. Okay, you're welcome. I can see who just joined. Okay. All right. In the next 3 minutes, you are starting. Please share the link with your friends. Okay, yeah, we are 4. Whether my numbers are not correct, I'm seeing 4 persons here. So it seems you're going to be starting very soon. So we have 2 more minutes by my time. We have 2 more minutes. Please, I want to believe I'm audible. Am I audible enough? Please, if I'm audible enough, drop a comment. Drop a comment, sir. I can hear you. I can hear you. Drop it on the comments. I want to see that. Okay, teenager. Beautiful. Thank you. Teenager, thank you. Beautiful. So I'm audible enough. So today we are going to be starting from chemical kinetics. Now, if you look at what I have here, I have 5 questions on each of the topics. Yesterday, we treated 5 questions on stoichiometry. And today we are going to start from chemical kinetics, rates of chemical reactions. So we are going to be solving 5 problems or unavoidable problems from there. After which we'll be solving 5 problems from thermochemistry and thermodynamics. So if you have enough time, you're going to be solving 5 problems from Lewis structures, molecular geometry, and dipole moment, alongside hybridization. So these are all what we have for tonight. So without further ado, let's begin, starting with chemical kinetics. Are you ready? If you are ready, type yes in the comment section. I am ready. Type I am ready in the comment section. Let's start. Beautiful. Yes, from Dara Solo. Okay, today's session promises to be very, very interactive. You're really going to enjoy this one. You are really, really going to enjoy this one. So without wasting much time, I'll be solving the very first problem on the series, chemical kinetics, rates of chemical reactions. So I'll be solving question number 1, which says, the rate of a chemical reaction will be affected by the following except. Now the options I have here, I have option A, temperature at which the reaction occurs. Option B, concentration of products. C, surface area of solid reactants. And D, concentration of catalyst. Now, from our previous classes, we talked about factors affecting rates of reactions. And among those factors, we never talked about the concentration of products. So the concentration of a product does not have any effect on the rate of a reaction. What has an effect on the rate of reaction is the concentration of the reactant, or let's say the concentration of the starting reactant. All right, so the correct answer to number 1 question is option B, concentration of products. Remember, the question says the rate of a chemical reaction will be affected by the following except. So the answer is option B, concentration of products. Beautiful. I can see the answers in the comments. That's good. Let's go to question number 2. Now, for question number 2, we are going to be applying the integrated rate law for a first order reaction. Question number 2, it says, the decomposition of N2O5 to NO2 and O2 is first order with a rate constant given at temperature 45 degrees Celsius. Now, the question says, if the initial concentration is given here, what is the concentration after 825 seconds in mole per liter? Now, this is a sample exam problem which we can solve within a space of 1 minute and we get our answer. So how do we solve this problem? Now, remember, this question is a first order reaction question. So we are going to use this formula. Let's write it out. So I'm going to be using this formula here. So this is my formula. I'm going to be using this formula. It says lane concentration of divided by the concentration 0 is equal to minus kT. So I'm going to be using this formula to solve my problem. Now, what is the meaning of the terms I have here? Now, the AT represents the final concentration of A. Now, while my A naught represents my initial concentration of A. So these are the things you need to know before solving this problem. Then the K here represents the rate constant. So this is the rate constant, K, and the T here represents the time. All right, so this is the formula we're going to be using to solve this problem. Now, how do we solve the problem? Now, let's figure out the given parameters. Let's go back to the question. The question says that we are given a rate constant of 4.8 times 10 raised to the power minus 4 per second. So our K, so given, we have 4.8 times 10 raised to the power minus, let me check it again. Yeah, minus 4 second minus 1. So that is the value of our K here. That's K. Then what else is given in the problem? Let's check to the problem again. We are given that the initial concentration of A is 1.65 times 10 power minus 2. So we are given that A naught is equal to 1.65 times 10 raised to the power minus 2 mole per liter. All right, what else are we given in this problem? This problem also gives us something. It says, what is the concentration? That means we are looking for AT. We're looking for AT unknown. So what else are we given here? Now we are told What is the concentration after 825 seconds? So our time here, T, equal to, our time T is equal to 825 seconds. So how do we solve this problem? Let's start solving the problem. So to solve this problem, we are not going to use the first equation we have here because the first equation contains natural logarithm. And what you are looking for here, you are looking for AT. So to find AT, we have to use a second equation. I'm going to call this equation equation 1. So now my second equation is going to be when I take the exponential of both sides, eliminating the natural logarithm. So I'm going to have that AT over A naught is equal to exponential minus KT. Now, with the formula I have here, I can easily make my AT the subject of the formula. And when I do that, I am going to get my final answer. So let's substitute. So I'm going to have that my AT is going to be equal to cross multiply. We have that A naught exponential minus KT. So carefully substitute all what you have and you get your final answer. Let's do that together. So what is my AT going to be? What is my A naught? I have 0.65, which is same as 0.0165 multiplied by exponential. Now, exponential in your calculator is the second function of natural logarithm, ln. So you click on shift and click on ln. That gives you exponential. Then you open up a bracket and put in your k and your t. So I have minus. So what is my k? My k is 4.8, which is 0.00048. All right. 1, 2, 3, 4. Correct. So multiply by what now? I have, what's my time? My time is in seconds. That is 825. All right. Put this in your calculator, and that's going to give you the final answer to this question. And what is it going to be? Now, have you done this? If you've done it, put it in the comment section. Let me see your final answer. Do this in your calculator. Let's see your final answer. After that, I'll do a little analysis on that problem. Now, do that in your calculator. Let's see the final answer. Okay, you are not, somebody saying you are not seeing. What are you not seeing? Are you not seeing what I'm solving? Please, I want to be sure. Check whether you're seeing what I'm solving. Check. Are you seeing what I'm solving here? Check. If you are seeing what I'm solving, drop yes, I'm seeing in the comment section, please. David Christopher, we are not. I want to be sure. Are you seeing what I'm solving? Please drop it in the comment section. Yes, we are seeing. Okay, correct. Somebody saying yes, sir. David Christopher, you can now see. That's beautiful. All right, so now punch this in your calculator. Let's have the final answer. What will you get from here? What will you get from here? So if you are with your calculator, punch it. Let's see. 0.0111. That's beautiful. From Joshua Christopher. That is beautiful. All right, so this is going to give us 0.0111. What's the unit here? Mole per liter. Final answer. Now, if you check the options here, what do you think is the correct option here? Look at the question and tell me the correct answer. Check. What's the correct option? Type it in the comment section. I want to see it. Type the correct answer in the comment section. Let me see it. Type the correct answer. Okay. Type the correct option. Let's see the option now. I want to be sure you are seeing this question here. What's the correct option here? Is it A? Is it B? Is it C? Is it D? Is it E? I check. All right, the answer is option D. I'm seeing a D in the option. Yes, that's the correct answer. Option D. That's correct. That is correct. Now, don't join us on time. towards the end of the life, I'll come back to this problem and I'll solve it again. So let's move on to the next question now. Question number 3. Are you ready? Are you ready? Question number 3. All right. I want to be sure you're seeing question number 3. Are you seeing question number 3? Are you seeing question number 3? All right. Let's solve question number 3 now. Question number 3. Beautiful. No. That answer I'm seeing from, who is this person? From Tiene. That's not correct. Okay, Teenager is correct. Okay. Okay, you are not seeing the question. Look at the question here. The question is very clear. We are now on question number 3. Look at number 3 here. Is number 3. We are now on number 3. Now I'm going to read the question out again for everyone to hear. I'm reading it again for everyone to hear. Beautiful. Yeah, David Christopher, 0.0111. You're correct. You are very correct. You are very correct. Now let's go to question number 3. Now, if you are with me, I'm moving right forward. Question number 3. All right, option D is correct. Option D is correct. Yes. All of you are doing very well. That's the answer. So let's go to question number 3 now. Let's go to question number 3. So question number 3 says, a reaction of the form AA to give products is second order with a rate constant given here. What is the half-life in seconds if the initial concentration of A is 5.25 times 10 raised to the power minus 3 mole per liter? Let's do that together. I want to be sure you heard me. Let's solve problem number 3. Problem number 3. Let's solve problem number 3. Okay, so what are the given parameters for problem number 3? Now, for problem number 3, we are considering a reaction of the form. Please, I want to be sure everyone is seeing what I'm solving here. Okay, so we are considering a problem. We are considering an equation that looks just like this. You have A to give you products. Okay, now from this equation, what do we have? We are told that from the question that this is a second order reaction. Now check this out. It says is second order with a rate constant of that. So let's figure out the given parameters. So we have a rate constant K. My K here is giving us 0.413 liter bracket mole dot second. All right, so these are my given parameters. So I have K given here. Now let's continue checking out the given parameters here again. Now we're told if the initial concentration of A is 5.25. So I have that A naught is equal to 5.25 multiplied by 10 raised to power minus 3 mole per liter. So this is the initial concentration of A. Now the question is asking us to find the half-life in seconds. So we are going to find the half-life in seconds. Now the question is this: what is the half-life for a second order reaction? What is the formula for the half-life for a second order reaction? Let's check it out. So for a second order reaction, the half-life is giving us 1 over Ka naught. Check it out. So half-life T half is equal to 1 over Ka naught. Now, what does this formula mean? This formula tells you that To find the half-life with respect to a second order reaction is going to be 1 over the rate constant multiplied by the initial concentration. So this problem is quite easy. So we're going to substitute all the given parameters here and get our final answer. So my T half is going to be equal to 1 over, what is my K? My K is 0.413. K is 0.413 liter. Okay, we know the unit already. Multiplied by, what is my initial concentration here? My initial concentration is 5.25 multiplied by 10 raised to power minus 3. All right. Now, someone should punch this into the calculator. Let's have the final answer in seconds. What is our final answer in seconds here? What is our final answer in seconds? Final answer in seconds. I'm waiting. What is our final answer in seconds? So we are working on 1 divided by 0.413 multiplied by 5.25 times 10 to the power minus 3. So what's the final answer in seconds? Am I seeing 461.2 seconds there from Joshua Christopher? Beautiful. That is the correct answer. 461 seconds. 461 seconds. All right. Now let's check the correct option from here. Now look at the question properly and tell me the correct option from here. What is the correct option? Drop it in the comments. Let me verify that. Drop it in the comments. Let me verify that. I want to be sure you are seeing this. All right. That should be option what? Option A. All right. Option A. Option A. Option A. Option A. All right. Option A is the correct answer. 461 seconds, approximately. If you have any problems with respect to question number 3, drop it in the comments. Let me respond to that before going to question number 4. All right, A is correct. Option A is correct. Option A is correct. Option A is correct. Okay, now question number 4. Now, I would like you to take about 30 seconds of your time, or let's say just use a minute. Look at question number 4 very well, the answer, before I start talking about it. Check out question number 4. You have 1 minute. Okay. 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 Any answers yet for question number 4 before I begin? Let me see the comments. It's clear now. All right. Okay. Any answer for question number 4 before I begin? All right. Let me begin immediately. So for question number 4, let's solve the problem now. The question says, a reaction A plus B plus C to give us D plus E has a rate law. Rate is equal to K into A squared B. Which of the following changes will have the least effect on increasing the rate of the reaction? Okay, now I'm going to rewrite the rate law. I want you all to see the rate law here given for this reaction. So this is the rate law for reaction. The rate law for that reaction is giving us rate is equal to K into A squared, and you have B. So this is the rate law for that particular equation. Now let's analyze that equation. Don't forget that the original equation of the reaction, which has that rate law, is A plus B plus C to give us D plus E. So this is the original equation which gave birth to this rate law. Now let's analyze the question. So the question says, let me come back to it. The question says, a reaction A plus B plus C to give us D plus E has rate law this. Which of the following changes would have the least effect on increasing the rate of the reaction? So this question also points to rates of chemical reactions. Now look at option A. Says doubling A naught while keeping B naught and C naught at constant. Option B, doubling B naught while keeping A naught and C naught constant. Option C, doubling C naught while keeping A naught and B naught constant. And option D, increasing the temperature of the reaction. Option E, adding a catalyst. Now, which of these factors here is going to have the least effect on increasing the rate of the reaction? Now, before we can answer this question, let's look at the rate of the reaction again. Now, check this out. From the given rate law, we can see that the original reaction contains reactants such as A, B, and C. Now, coming back to the rate law equation, which is given here, from the rate law equation, I cannot find all the reactants in the rate law. What does that mean? Now let's look at the rate law. For the rate law, we have A is part of the rate law. We have that B is part of the rate law, but C is not part of the rate law. What does that mean? Any particular reactant that is not part of the rate law, it is very, very clear and significant that increasing the concentration of that particular reactant will not have any effect on the rate of the reaction. Let me take it again. I said, anytime you are given a rate law equation just like this, now you check and you there are some reactants that are not part of that rate law. It's very clear that those reactants, no matter how you increase their concentration, they will not have any effect on the rate of that reaction. So in simple terms, those reactants are said to have a zero in the rate law. Okay, so now we can see that since C is not part of this rate law, it is very obvious that C has a zero order. And don't forget, from mathematics and from law of indices, anything raised to the power of 0 is equal to 1. So this question can come in different ways. They can be asking you, what is the rate, or let me say, what is the reaction order for reactant A? The answer is 2. What is the reaction order for reactant B? The answer is 1. What is the reaction order for reactant C? Now, since reactant C is not part of the rate law, the reaction order is going to be equal to 0. All right. So let us now go through the options to figure out the correct answer to this question. From the options here, the correct option is going to be option C. Option C says doubling C naught while keeping A naught and B naught constant. Let me spell something out. Now, the A naught you are seeing here and C naught and B naught, they represent initial concentrations. All right. So the correct option is option C. So when you double C naught while keeping A naught and B naught constant, it will not have any effect on the rate of the reaction. Now, going through the other options, option A, B, D, and E, these options will have a significant effect on the rate of the reaction. So our correct option is option C. If you have questions here, feel free to ask. Okay, I can see option C in the options. Yeah, okay, in the comments. Yeah, Abbasian, option C, that's beautiful. All right. Rosaline Ekpo, option C. I'm so proud of you guys. I'm super proud of you guys. Now, let's go to question number 5. Let's go to question number 5, and that will be the last question under chemical kinetics. Then we are going to be moving straight to thermodynamics and thermochemistry. Question number 5. So each of the questions, I'll give you a minute to look at the question, and let me see your answer from there. Now look at question number 5. I want to be sure you are seeing question number 5. If you are seeing question number 5, let me see it in the comments. Say, I can see question 5. I want to be sure question 5 is very visible. Check question 5. Can you see question 5? I need the responses in the comments. If you can see question 5, drop a response in the comments. I want to see. Beautiful. Beautiful, Loretina. Beautiful. All right, let's solve it together now. Now I'm going to give you 1 minute, that's 60 seconds. Look at the question, decide an answer before I come in. 60 seconds. Okay, what are your answers? What are your answers? Okay, to question 5. 5 is very technical, and I'm going to do it for you. You're going to love it. I'm seeing Duke Hope is saying A, option A, 102. Beautiful. You still have like 24 seconds more before I come in. 24 seconds more before I come in. $24 more before I come in. I'm seeing option C here. Okay. You're trying your best. I love what you're doing. Keep trying. Keep trying. I'm here with you. Keep trying. Who are those living? Okay. Keep trying. You're doing well. Option C, sir. Okay. That's from Joshua Chris. All right. You are doing very well. You are doing very well. So I'm going to use question number 5 to show you something, or let me say to teach you something very, very vital under chemical kinetics. Question number 5. Okay, time up. Time up. Now let's solve it together. Let's solve the problem together. Now, in the end, you're going to decide whether you were correct or you're wrong. So let's solve together. Question number 5 says, you perform some experiments for the reaction A to give you B plus C and determine the rate law has the rate. Now look at it. Now, let me write it out now. For question number 5, you are given that the rate law is given as rate is equal to K into A into what? X. Let's solve AX. Now the question says, calculate the value of the exponent X for each of the following conditions. Pay attention to this. Calculate the value of the exponent X for each of the following conditions. Condition 1, A is tripled and you observe no rate change. Condition 2, A is doubled and the rate doubles. Condition 3, A is tripled and the rate goes up by a factor of 27. Now, this is one of the simplest problems we are going to solve in our class today. Okay, so this is one of the problems, one of the most simplest problems we're going to solve today. Now, this is how to solve the problem. Pay attention here. Pay attention. All right, now, if this is the rate of a reaction, pay attention. Now, pay attention. Now, this is the concentration of A raised to power X. So we can say that the order of this reaction is X order. That's X order reaction. So now, if you decide to double the concentration of A, what effect is it going to have on the rate? Pay attention here. So if I should double the concentration of A, what do you think is going to happen to the rate? What will happen to the rate? Now, this is the mathematics here. Now, doubling simply means multiplying something by 2. Doubling means multiplying something by 2. Is that not correct? So since I'm doubling, what is going to be the effect on the rate of this reaction? So as you are doubling, don't forget that the concentration of A is raised to power X. So as I'm doubling, the effect on the rate is going to be 2 raised to power X. If I decide to triple the concentration of A, I'm going to have this. Tripling means Tripling means what? You are multiplying by 3. So I have a 3 here. Tripling means multiplying by 3. So what effect will tripling have on the rate of the reaction? Now, this is the effect on the rate of the reaction. Tripling is going to have an effect of 3 raised to the power to which my A is to here, and that will be X. Now, let's now go back to the original problem here. Look at the original problem. It says condition 1. Condition 1 says A is tripled and you observe no rate change. Now, what can make A to be tripled and there is no rate change? Now, if I triple A, if A is tripled and there is no rate change, now there is only one indication there. And what's the indication? That the X here is equal to 0. Now, what does that mean? Check this out. So if I should triple means you are multiplying by 3. So what effect is it going to have on the rate? It's going to have an effect of what? 3 raised to the power what? X. Now, the question says you tripled and in the end, you notice that there was no effect on the rate. What does that mean? That simply tells you that the power of X here is equal to what? 0. Now, when the power of X is equal to 0, from law of indices, anything raised to the power of 0 is equal to 1. Is that not true? That simply means as you tripled here, it gave you 1 on this side, meaning that there is no effect on the rate. So therefore, it's just like saying rate multiplied by 1. Or you say rate multiplied by 3 raised to the power 0. And which is equal to what? Rate. So when rate is multiplied by 3 raised to the power and it gives us rate, it simply means that it did not, let me say, it does not have any effect on the rate. So for the first situation, that is our I, for situation I, the order of the reaction there is equal to 0. Now let's go to the second case. For the second case, look at what you have for the second case. Case 2, it says A is doubled and the rate also what? Doubles. What does that mean? Now we are saying that rate is what? Let me say A is doubled. Doubling means multiplying by 2. We are going to multiply by 2. So as I'm multiplying by 2, what will be the effect on my rate? Now my rate here, I'm having X as my power. So what will make the rate to also double? Now in that case, X is going to be equal to 1. Meaning that if I double my concentration of A, my rate also doubles because 2 raised to the power 1 is equal to 2. So therefore, as I'm doubling my concentration, my rate is doubling. As I'm tripling my concentration, my rate is also tripling. So therefore, in that case, that is case 2. I have that x is equal to 1. So we have two cases now. That's case 2. Case 2, x is equal to 1. Case 1, x is equal to 0. Now let's go to case 3. Now for my case 3 says A is tripled and the rate goes up by a factor of 27. What does that mean? Now, if I should triple my A, what will be the effect on the rate? Now, my rate is going to what? Have this same effect here, 3 raised to the power x. Now, what is going to make it to be multiplied 27 times? In that case, my x value is going to be equal to 3. Meaning that if I should insert the 3 here, I'm going to have 3 raised to the power 3 gives me 27, because 3 times 3 is 9, and 9 times 3 is equal to 27. So in that case, my x is equal to 3. So what does that mean? So the correct answer to this question should be an answer that responds to 0, 1, and 3. Let's check the correct answer now. Let's check the options. So from the options, what is the correct answer? From the options, what is the correct answer? 0, 1, and 3. The answer is option B. Option B, 0, 1, and 3. I'm expecting questions from the comments. All right, I'm seeing responses from Rosaline Ebo, option B, correct? I'm seeing Abasiene John, correct, B. All right, you guys are doing very well. You guys are doing very well. You're doing fantastic. Okay, somebody is saying, I don't understand. All right, now let me explain from first principle. Now, I want you to pay attention to this. I want you to pay attention to this. So I'll be using another example to, to illustrate what I'm going to give to you now. So watch this. Watch this. Now, let's say you are given the rate law for a reaction. Now, check this out. Now, this is the rate law for a reaction. So the rate law is giving us rate. Rate is equal to what? K. Pay attention. K into what? Let me use A. Let me use A here. A. Let me use B here. B squared. Yeah, B squared. Now, let's look at this particular rate law equation. Now, let's say you are asked question number I. If you double the concentration of A, what effect will it have on the rate of the reaction? What effect on the rate? Now, we all know that doubling simply means you are multiplying by 2, right? Okay, so if I should double the concentration of A here, how is it going to affect the rate of the reaction? Now, before you answer that question, you have to check this rate law equation and check what power is A raised to. That's the question. What power is A raised to? Now, if you look at this place now, A is raised to power 1. Now, anytime something is raised to power 1, you notice that nothing will be written there. So the power here is equal to 1. So A is raised to power 1. So if I should double A, doubling means multiplying by 2. Now, what is the power of A here? The power of A is equal to 1. So 1. This will be the effect on the what? Rate. So what does that mean? That simply means if I should double the concentration of A, my rate is going to also what? Double, because 2 raised to power 1 is equal to 2. So doubling the concentration of A also doubles the rate. So now take note. If you double the concentration of something and the rate also doubles, it's very clear that reaction order of that particular reactant is equal to 1. So when the reaction order, or let me say when the order of the reactant is equal to 1, once you double the concentration, the rate also doubles. If you triple the concentration, the rate also what? Triples. If you should quadruple the concentration, the rate is also going to be what? Quadrupled. Now let us also analyze this with respect to reactant B. Now, what will be the effect? What will be the effect if you double the concentration of B? Now, when the concentration of B is doubled, what do you think is going to be the effect on the rate of the reaction? Now, I would like you to learn this because it's going to help you in the exams. So if you double the concentration of B, what will be the effect on the rate of this reaction? Now, don't forget, doubling means multiplying by 2. Now, going back to the rate law equation, B as a reactant here has a power 2. So if I should double the concentration of B, now the effect on the rate is going to be 2 raised to power 2 because the power here is equal to 2. Doubling means 2, and the power on B is 2 on the rate law. So therefore, the rate is going to be affected by this factor. Now, and what factor is this? This is equal to 4. So hence, if I should double the concentration of B, the rate is going to increase 4 times. Because on the rate law equation, B has a power of 2. Now let's talk about tripling effect, because I believe you now understand doubling effect. So let me just write it down. Doubling the concentration of B increases the rate by a factor of 4. Or you can simply say it increases the rate 4 times. Now, what happens when you triple? Now, let's talk about tripling effect. Now, I would like you to answer that question in the comments. Now, let me just drop the question. The question says, if you triple the concentration of B, what will be the effect on the rate? I'm waiting for your response in the comments. You have 20 seconds to drop the answers, then I will help you from there. So if I should triple the concentration of B, what will be the effect on the rate of the reaction? Drop your answers in the comments. Let me see. Drop your answers in the comments. I want to see. Drop your answers in the comments. I want to see. Tripling the concentration will cause the rate to be increased by 9. I love that. Rosaline Epo, you are doing a very fantastic job. The answer is going to be 9. Let's wait for other responses. Okay, now I have a response. The answer is 9. Now check this out. So if I decide, pay attention, if I should decide to triple B, or let me say the concentration of B, this was going to happen to my rate. Now, because B already has a power of 2 in the rate law equation. So if I should triple means multiplying by 3. So I'm tripling now, tripling. So if I should triple, now B has a power of 2 here. So now the effect on the rate is going to be 3 raised to the power 2, which is equal to 9. So if I should triple the concentration of B, my rate will increase 9 times. Or you say rate will increase by a factor of 9. So this is how to solve problems like this. Now, if you should narrow this down to the question we just answered, you notice that from that question we just answered, it is very, very simple. Now, let's marry it with this question here. Let me place it side by side. So now let's marry it with question number 5. Look at question number 5 here. It says, you perform some experiment for a reaction, whatever, to determine the rate law, has the rate this. Rate is equal to Ka into what? X, raised to power X. Now, calculate the value of exponent X for each of the following conditions. Now, under exam conditions, we will not need to spend up to 2 minutes solving this problem. It's very, very simple. Now, condition 1, it says A is tripled and you observe no rate change. This is the simplest. Now, if A is tripled and you observe no rate change, what does it mean? It simply means that the order, or let me say the value of X is equal to 0. Because when you triple something and raise it to power 0, it gives you 1. And when you multiply something by 1, it gives you the exact same thing, meaning that the power of X, or let me say the value of X is going to be 0 in that case. Now, if you should go to the second condition, condition 2, it says A is doubled and the rate also doubles. Now, when you double something and the rate also doubles, it is a clear indication that the value of X in that case is equal to 1. Because when the value of X is equal to 1, if you double, it also gives you 2 on the other side. Hence, X is equal to 1 in that case. So we've considered 2 cases now. The first one is 0 and the second one is 1. Now let's now go to the second, or let me say the last case, that is case 3. Case 3 says A is tripled and the rate goes up by a factor of 27. A is tripled and the rate goes up by a factor of 27. Now you ask yourself, now what are you going to raise 3? Or what power are you going to raise 3 to get 27? The answer is 3. So in that case now, X is equal to 3. Because 3 raised to the power 3 is equal to 27. So the correct option here is option B, 0, 1, and 3. Let's now solve problems on the next topic for today. So the next topic for tonight, we are going to be covering problems on thermochemistry and thermodynamics. Problems on thermochemistry and thermodynamics. If you are following me, I want you to respond, I am following. Then if you are not following, respond, I'm not following. This is where I don't understand. I want to see it in the comments before I proceed. No responses in the comments. I am following. I love that. I am following. Okay. Joshua Christopher, Doretina. Okay. Rosalind. All right. Understood. Proceed, sir. Thank you very much. So I can now proceed. So let's talk about problems on thermochemistry and thermodynamics. Thermochemistry and thermodynamics. So the very first problem under this segment is, it goes like this. In which of the following systems is neither energy nor matter exchanged with the environment? Drop your answers in the comments. I'm waiting. In which of the following systems is neither energy nor matter exchanged with the environment? Drop your answers in the comments. Beautiful. Rosalind Ebo, the answer is an isolated system. So an isolated system exchanges neither energy nor matter with the environment. Now, this will also attract you to look up types of systems in thermodynamics, where you talk about closed systems, open systems, adiabatic systems, etc., etc. So you check them out. Now let's go straight to question number 2. Now for question number 2, I would like us to answer this question critically. Question number 2 says, if in an experiment, 1 mole of methane burns in oxygen and evolves 890 kilojoules of heat. What type of reaction is this? What is the heat of reaction? Two questions in one. What type of reaction is this? And what is the heat of reaction? Now let's do this. Let's do this. What type of reaction is this? And what is the heat of reaction? Now, since the reaction evolved heat, now when you say that something involves heat, it means that heat is leaving from the system into the surroundings. And any reaction that follows that pattern is called an exothermic reaction. And for exothermic reactions, the value of delta H is equal to negative. That is for exothermic reactions. While for endothermic reactions, we have positive values of delta H. Now let's come back to the question. The question says, what type of reaction is this? So the answer is what? Exothermic. The answer is exothermic. And the second part of the question says, what is the heat of reaction? What is the heat of reaction? Okay, a lot of you have the answers already. So the heat of reaction is going to be the negative value of 890 kilojoules. So the correct option here is option, let me see, option B. Yeah, you're correct. Exothermic, and Q is equal to minus 890 kilojoules. Let's go to question number 3. Now, check out question number 3. Use about 3 minutes, or sorry, not 3 minutes. Use about 30 to 45 seconds to figure out the correct answer. Then I'll come in. Maya in 1. I'm seeing B. I'm sure that B is for question number 2, not 3. So I'm waiting for responses for question number 3. Responses for question number 3. Responses for question number 3. I'm going to teach you something very special in question number 3. Are you ready? I'm seeing B all through. Are you sure? Are you sure? All right. Okay, time up. I wouldn't want us to waste much time today. This is already 58 minutes. In the next 5 to 10 minutes, we'll be ending this session so that we'll have our last session tomorrow for the last 2 topics. Okay. All right, so let's solve question number. Someone says option A. All right. You guys are okay. Let's solve the problem to know the correct answer right away. Now, to solve that problem, there are some formulas you need to understand. And the formula you need here is coming from the first law of thermodynamics. The first law of thermodynamics states that change in internal energy, which is delta U, is equal to the sum of Q plus W. Now, what does this equation mean? It means change in internal energy of a system, just like a system that contains gas, the system we used in class the other day. Now, the change in internal energy is going to be equal to the sum of the heat alongside work. So I'm going to sum up heat and work. All right. Now, let's analyze this equation properly before we understand what it means. Now, from this equation here, we have Q. Q means heat. And don't forget that heat here is a form of energy which can take either positive forms or negative forms, depending on whether the heat is absorbed or whether the heat is evolved. Now, pay attention to this. Now, when the heat is evolved, Q is equal to what? Negative. Now, when the heat is absorbed, Q is equal to positive. So these are the two conditions you need to understand with respect to heat. Let's now talk about work. Work, W. Now, we have two forms of work. Number one, work done on the system. And we have what to call work done by the system. Now pay attention to this. Work done on the system is positive, and work done by the system is negative. Take note. Work done on the system is positive, and work done by the system is negative. What does this mean? Now, if work is done on the system, for example, you have a piston in a cylinder. Now, if this is a cylinder here, this cylinder contains gas. There's gas here. There's gas in my cylinder, and I have a movable piston here. Now, this piston has the job of pushing this, pushing this. Now, when the piston pushes this gas, it compresses it, meaning that there's an external work that is done on the system. So let's assume that somebody just pushes the piston, and the piston begins to compress the gas. What's going on there? Now you can see that work, because the system under consideration here is a system that contains gas. So therefore, work is done on this system. And from the sign convention here, that work is what? Positive. Then on the second condition, when work is done by the system. Now the gas in the container here can decide to expand. When the gas, it begins to push the piston up. And in that situation, work is done by the system. Now the gas is now doing work by pushing the piston up. And in that case, the work done by the system is negative. That's a sign convention. Now take note. Work done on the system is positive, and work done by the system is negative. All right, now, since we now understand all these, let us now solve problem number 5. Problem number 5 says, let me check. All right, yeah. Problem number 5 says, oh, sorry, problem number 3. We are not yet on 5. Problem number 3. It says, a gas expands. Pay attention to this. A gas expands and does work on the surroundings. Pay attention now. A gas expands and does work on the surroundings equal to 325 joules. I'm going to record my work. So the work done here is equal to minus 325 joules. Why is it minus 325 joules? Because it is the gas that did the work. So therefore, the gas did work against the surroundings, meaning that that is negative work. The system has now done work, which is negative. So I'll record it as minus 325 joules. Let's continue. Now it says, at the same time, it absorbs 127 joules of heat. Don't forget, heat absorbed is positive. All right, so we have that. Our Q here now is equal to plus, let me get that value again, plus what? Plus 127 joules. So plus 127 joules of heat. Now let's substitute back into the original formula. So we have that. Before we substitute, let's check what the question is looking for. The question says, calculate the change in the energy of the gas. So we are looking for delta U. So delta U here now, delta U is equal to, now my heat Q is 127, is positive. All right, plus was in the original equation, plus, now I'm going to open a bracket here. because my work is what? Minus 325 joules. These joules here. I'll close the bracket. So what is my final answer? So I'm going to have plus 127 joules plus multiplied by minus is minus 325 joules. I'll have a negative answer. And what is the final answer? Drop it in the comments. Let me see. Drop it in the comments. Let me see. What is the answer? What is the answer? Correct. The answer is minus 198 joules. That's option A. So minus 198 joules. That is option A. All right, done. Now, if you have questions on this, please drop it in the comments. I want to see. If you have questions on this, drop it in the comments. Let me see. Questions on that. Questions on that. Questions on that. Drop it in the comments. Let me see. Okay, it seems we don't have questions on that. All right, now let's take a vote. Now, do you think we should complete the remaining chapter, or do we have another live tomorrow to complete it? Do you think we should complete the remaining chapters? We have just one chapter left. That is hybridization, molecular geometry, and all that. Yes, definitely. Yeah, definitely. I'll record this section and I'll work on it and I'll post it. All right. So I need your suggestions. Do we? Okay, let's complete it. I'm seeing okay, if you want us to complete it, drop, let's complete it. If you want us to end the live, drop, let's end the live and continue tomorrow. I want to see your comments. Okay, I've seen 3 completed. Complete it. Okay, complete it. Oh my God, I don't have enough data. Oh, who is this teenager? You don't have data. It's all right. Okay, I think I have to, let me see. Let me check. It's okay. So let's just complete question number 4 and 5. After completing question number 4 and 5, the remaining topic will be done tomorrow. So let's complete question number 4 and 5. Now pay attention to this. I want you to pay attention to question number 4. Now, question number 4 involves very simple logic. Very simple logic. Very simple logic. Please pay attention. So question number 4 says, bond breaking reactions are often dash, while bond forming reactions are often dash. Let's provide the answers to this question. 20 seconds to provide the answers. Okay. Let me give you 30 seconds to provide the answers. Okay. All right. So now I want you to pay attention to this analysis. Now, in a chemical reaction, just like this, let's say there's a reaction like A plus B to give us C plus D. Now, in every chemical reaction, we normally say that old bonds are broken and new bonds are formed. Now, this question is asking us, bond breaking reactions are often dash. Pay attention here. Now, what is involved in breaking bonds? Now, for example, let's say we have a bond existing between A and B. How do you think you are going to break this bond here? Now, before you can break this bond, you need some amount of what? Energy. So therefore, energy must be what? Used to break this bond. So in other words, energy must flow from the surroundings into the what? System before a bond can be broken. So what does that mean? That simply means that bond breaking reactions are basically endothermic, because before a bond can be broken, energy is required to break the bond. So the required energy implies that the system will need to absorb energy either in the form of heat or whatsoever to break the bond. So since the system will need to absorb heat to break that bond, it is very obvious that bond breaking reactions are endothermic. What about bond forming reactions? Bond forming reactions are exothermic because when bonds are formed, heat is released. Pay attention to that. You can jot it down. So whenever bonds or whenever new bonds are formed, heat must be released in the form of energy. Take note. Or let's say energy will be released in the form of heat. So the correct answer to this question is option A. Oh, no, option, not A. It's option B. Endothermic, exothermic. So the correct answer is option B, endothermic, exothermic. So we are done with question number 4. We are now going to solve the last problem for today's live session. The last problem for today's live session. So if you don't mind, you can look at it here before I provide the answer. So I'm going to give you 30 seconds as usual. Check it out. Is this something you can do? Check it out. Then we'll do it together. Is this something you can do? You have 20 seconds. Okay, now let's provide the answer to that question. Sir, please remove the pen. Oh, sorry. I've removed the pen. The pen is out. Okay, so what do you think is the correct answer there? Now let's solve the problem together. Now this question you are seeing here is a typical example of how to apply stoichiometry to the heats of reactions. Applying stoichiometry to the heats of reactions. Now let's analyze this problem step by step. So while you're looking at it, I want to believe you can see it. So while you're looking at it, let's solve the problem right here. Okay, I'm solving the problem right away. Let's solve it. Now the question says, how much heat has evolved when 9.07 times 10 raised to the power 5 grams of ammonia is produced according to the following equation? Now in bracket, assume that the reaction occurs at constant pressure. All right, that's okay. Now let's look at the question. Let's look at the equation of reaction. Look at the equation of reaction. We are given that N2 plus 3H2, that's the balanced equation, to give us 2NH3. And delta H for this reaction is giving us 91.8 kilojoules. 91.8 kilojoules is the value of my delta H. Now, I need to be very sure that there is no minus sign here. Okay, sorry. There's a minus sign for the delta H. So delta H is minus 91.8 kilojoules. That's the value of delta H. There's a minus sign there. So this is an exothermic reaction. Exothermic reaction. Now the question says, how much heat has evolved when 9.07 times 10 raised to the power 5 grams of ammonia is produced according to the following equation? Now let's check this out. Now from this equation, We are considering ammonia. Please pay attention. We are considering ammonia. Check this out. So from this equation, what is the molecular weight of ammonia here? Or let's just say that when 2 moles of ammonia was produced, 91.8 kilojoules of heat was evolved. Very simple. So look at it here. When 2 moles of ammonia was produced, minus 91.8 kilojoules of heat was associated with the what? Reaction. Or you can say that 91.8 kilojoules of heat was evolved, whatever. So this is our statement. Now, this statement you are seeing here, you are going to convert this statement to what? A mass interpretation. Now, what is the molecular weight for ammonia? It is 17. So 2 times 17 is what? 34. So therefore, you can say that 34 grams of ammonia, when it is produced according to that reaction, we have that minus 91.8 kilojoules of heat was associated with the reaction, or 91.8 kilojoules of heat was evolved. What does that mean? Now, from here, you can say that, or let me say, we can now find what the question is looking for. The question is saying, how much heat has evolved when 9.07 times 10 to the power 5 grams of ammonia is produced according to the following equation? So therefore, you say 9.07 times 10 to the power 5 grams of ammonia, when it is produced, how much heat is going to be what? Associated with it. Now, in this case now, you are going to just do a simple cross multiplication to get your final answer. Now, you are going to what? Do a simple cross multiplication to get your final answer, and this is how to do it. So I'm going to say 9.07 times 10 to the power 5 multiplied by minus 91.8 divided by 34. And that will be 9.07 times 10 to the power 5 multiplied by minus 91.8 divided by 34. So whatever answer you get here is in kilojoules. Now, who has done it? Drop your answers in the comments. I want to see the answer now. What is the answer? You are correct. I've seen the correct answer in the option already. The correct answer is what? Minus 2.45 times 10 raised to the power 6 kilojoules. Now, it's very, very important you always take note of the sign of delta H. Now, let's assume that the sign of delta H here, let's say it were negative, it were to be negative. Or sorry, if it were to be positive here, our answer would have been a positive answer. But because it is negative here, our answer is going to be negative. Take note. So if our value of delta H were to be just plus 91.8, our answer would have been option B. But because it is minus 91.8, our answer is now option D. All right. If you have questions, drop it in the comments. This is going to be our last question for today. If you have questions, drop it in the comments before we conclude. If you have questions, drop it in the comments. We are about to conclude. Okay, questions. So why is it minus? Okay, now the minus 91.8 kilojoules is the value of delta H given in the question. Now look at it here. Is equal to what? Minus 91.8 kilojoules. So that's the value of delta H given there. All right, so that's the value given there. All right, now from the original problem, I made a slight mistake there. I forgot to add a minus. So there's a minus there. So I just corrected it. So there's a minus there. Okay. Okay, more questions. More questions, more questions, more questions, more questions. All right, so I can't find more questions in the comments. Sir, please, where can we find past questions? Now, guess what? All the problems you are solving here, we are all extracted from your past questions. We are all extracted from past questions. All right, so these are all past questions. That is why I tag this unavoidable exam questions, because these questions have been repeating for a very long time. So these are unavoidable exam questions. You need to look at them after now and see how you can solve them. All right. Someone is saying, sir, please, you've not answered my question from number 3. Which number 3 is that? Number 3 from where? Is it number 3 from thermochemistry and thermodynamics? Number 3 from where, please? Number 3 from where, please? Okay. Okay. All right. So we've really taken a lot of time, 1 hour 21 minutes. That's really fantastic. So we are going to finish up this live session tomorrow, and tomorrow we are going to be considering the last part of the live session, which is we are going to be considering Lewis structures, molecular geometry, dipole moment, and hybridization. So we are going to answer this time around no longer 5 questions. I'll make it 10. So we're going to answer 10 questions from Lewis structures, molecular geometry, hybridization. So thank you guys for coming around. I'm so happy to see you, and I'm going to see you again tomorrow. So do have a wonderful night. This is going to be the end of our live stream for today. So good night, guys. So I'm going to work on this video right now, and I'm going to post it so that you can watch it over and over again for better understanding. So good night. Do have a wonderful night. Yeah, good night, Rosalind. Good night, Loretina. Good night, Teenager. Good night, Duke. Good night, Joshua. All right. Good night, Crime Boy. Crime Beyond Borders. Good night. So why is okay? Okay, I've already answered that. All right. Good night, everybody. See you tomorrow.